Okay. Very good. Yes, so I will give a talk that's not going to go into the depth of the network on the supercomputers, but I will stay at a higher level, and I would like to discuss the exascale computing, what has been mentioned a lot, in particularly my colleagues at the DOD labs, of course, are very busy, because in the context of this initiative that President Obama signed last year, we see really a big investment in supercomputing, computing in general, in the US coming, in the coming years, and part of this initiative is, let me try to, so this, red one, okay. It is this accelerating the deliverability of capable exascale computing system across a range of applications. And so what I would like to reflect on is exactly what do we mean by exascale computing, or what exactly are we going to get when we see these machines coming at the beginning of the next decade. And so we can, and I want to become really quantitative about this, and in terms of applications, because this seems to be important according to this initiative. So today we measure performance of computers mostly in terms of this high performance Linpack benchmark. I will say a few things about this, but what we have, if we start today, we have machines, the top machines sustain, and I mean really the top in the top, 3 or 4, they sustain around 20 to 100 petaflops. And so if we take this based on the HPL benchmark, then exascale computing is only a factor 10 to 50 away from where we are today. And there are, of course, some questions about the productivity of these faster systems, namely, how long does it take you to really get the performance out in real applications? And I will say a lot about this today. So if we are saying, okay, we are not really using typically systems in the range of 20 to 100 petaflops, but surely, the top applications must be around the 10 petaflops today, and so we're a factor 100 away from exascale, and this is the number that I will be referring to. But you will see that it's not easy to even get the baseline of what we are doing today. This is a slide, of course, everybody knows the development of the HPL benchmark since it was introduced in the early 90s. And the most important point here, or actually 2 points. One is that there are actually applications that track this, benchmark. And the other one is that we see this 1,000-fold increase, which may now slow down over 10 years. But certainly when we look back the last 20 years, we see a 1,000-fold increase in sustained performance on the systems, the biggest systems that we have been running on. And I would like to stress again, this is not HPL. These are condensed matter physics or material science applications. The first time running at the sustained teraflop in 1998. This was a team at Oak Ridge, and then the team, again an Oak Ridge team, that was sustaining a petaflop in 2008. And so this is one way of looking at the metric. This is another way. So this plot I got from colleagues from ECMWF, the European Center for Mid-Range Weather Forecasting. I will say a lot more about them during the course of this presentation. And they've been tracking the sustained performance of their application on the machines they had. And you can, probably what you need to add here is, what I haven't is really looking at what would these applications be on HPL performance? How do they compare? But assuming they track similarly the top 500, what you see here is still an exponential increase. So this is a log scale over somewhere around 30 years. And, but when you do the numbers, you will see this is only a factor 100, only in quotes, because factor 100 every 10 years improvement in capability is bloody damn good. But when I compare it to the previous slide, there's a factor 10 discrepancy. So the question now is, are these machines, are the climate codes getting a factor 10 less efficient every 10 years? And that, of course, would be very depressing if it was that way. So, but the main, and we need to try to understand better exactly where the discrepancy is, and I'm not sure we really do, because these climate codes are extremely complicated, as we will see a little bit in the presentation. But the main thing is for us to take home is that application performance somehow has to be factored into the metric for supercomputing at exascale, and so I will try to use an example of real application, so a real domain, to explain what exactly is this application performance. And I can tell you, I'm not sure I can give you a final answer, but I will try to get, or in terms of a simple metric. But certainly what I will focus on is really applications as they are used today, and the example I'm using is in the weather and climate area, because I think this is one of the very important problems that is worth investing in hundreds of millions or billions of dollars. What you see here is a simulation that was again done by ECMWF, and this is since now the famous simulation of Hurricane Sandy and the prediction they made, that it would make landfall somewhere on the east coast. It turns out this prediction was right, and that's why we know a lot about it today, because it has been studied. So this was Hurricane Sandy. And what this basically shows is the importance of simulations at scale. And this is not just for scientific interest also. This is as a real economic and societal impact. And being able to predict where such a hurricane makes landfall and whether it does, really in the end saves lives and allows emergency teams also to really manage the situation much better. And just for practical matters to say, if you change the initial conditions slightly, what happens in this case, the forecast is the hurricane would actually not make landfall, but in this case, in this particular simulation, would go off into the Atlantic. And so what it really, in this calculation, what it comes down to is, first you need to have the capability to do these simulations in time, for it to be a forecast and not looking back, because the calculations end too late. But at the same time, you also need to run this simulation many, many times, and then they take the average, or they look at the distribution and then try to make a forecast where the most likely path will be. And then, of course, this gets updated. But the important thing is you want this to happen very early on, so several days before the hurricane makes landfall. And so the conclusion here is, before I come to the conclusion, what ECMWF also did very well is study the skill of their forecasts over the years, and then try to correlate the quality of the simulations with the underlying system. So you've seen in the plot before, they kept investing in larger and larger or more performant machines, and over time also the skill of their calculations has improved. And when you look at the specifics, so this is wind speed and precipitation, there actually is a correlation even not just with performance increasing, but also whenever they increase the resolution of the model. So this is a doubling or increasing the resolution. You can see afterwards the skill, certainly for precipitation in this case, increasing. So there is really a combination or a relationship between the resolution of the simulations and in the end the skills of the calculation. So we need, when we increase resolution, we talk about capability, improve the capability, but at the same time they also need to do these ensemble simulations, and so we also need throughput, so both. So exascale computers have to be able to do both, throughput and capability. And so we should, as supercomputing centers, not look just at capability. We really have to build systems that sustain, that can serve both. Okay, so I tried to make the case that we need higher resolutions. And this is from a discussion with colleagues, mainly Tim Palmer at Oxford University, but also colleagues at Max Planck, at ETH and Max Planck Institute for Metrology, and at ETH Zurich and ECMWF. And there is a general agreement that the quality of simulations that we need has to have a resolution of kilometer scale. And but that's one thing, the resolution. The other one is how much can you simulate in time. And so the severe weather predictions that we just heard is of the order of 10 days. If you do seasonal weather and climate predictions, then you have to simulate of the order of a year. And multi-decadal simulations of the order of 10 to 100 years, and predicting global predictions, informing mitigation policy for informing mitigation policies of the order of 100 to 1,000 years, and so on. So from this you can basically say, this is what we need to simulate at kilometer scale. And the relevant question is now, how long is the simulation allowed to take? And so the really relevant metric is this time compression, the ratio between simulated time and wall clock time. And in the case of this one, you want 10 days in a few hours in order to make a forecast for the weather, and so that means you need somewhere around the factor 100. And this is just numbers to say that, this is a hard problem to solve, but it is worth tackling this problem because it's, you can stack up the numbers it takes to mitigate the economic implications in mitigation. So it is really worth the investment. Now, today we do regional simulations on a refactored code, and this will be a big subject of this presentation, at kilometer scale and the time compression around 100. So this shows we can do these kilometer scale simulations today, at least for the weather applications. And I will say, go into much more detail and try to convince you that we can do this. And now we can say, if we do a global model, we just have to weak scale this, you build a bigger computer, and that's easy. There's no fundamental reason why you can't do this. In fact, the computers we use for weather are fairly small compared to the ones that, the fastest system on top 500. So it's absolutely feasible to do this today. But the problem is, in order to do climate, we have to increase the compression factor actually to 1,000, so factor 10 more, and then even more because of something called the spin-up of the models And so then we really talk about the factor 10,000, because you have to run very long simulations to set the parameters of the simulations first, and that has to integrate over timescales of the ocean, and so that's where quite a strong number comes from. So we have basically a factor 100 compared to what we are today. So this is comparable to the factor 100 we see promised by the Exascale initiative. But the big question is, what is the baseline of today's performance? Because here I'm talking about a refactored code. So I will now talk about this and tell you, try to explain what is involved in getting to this, what I believe is the baseline. But I will discuss this in more details. And the system I'm going to talk about, and this is good to talk about at the occasion of the MARC conference, is this GPU-based system that we introduced for Meteo Swiss. This is the Swiss meteorological service that is a member of ECMWF, and this is running a machine packed on with GPUs that was introduced last fall and is running on a Mellanox network, and we are working with DK on MVAPICH and using MVAPICH on this system. So the support from your group for this system is really fundamental, because this is this is in contrast to the research system. This system is really serious production. Has to be up and running all the time. And so on. So it has very different operational constraints and quality that we need. The model that they run on this is a community model. It's called COSMO. It is, for those here in the US, it is a comparable from a solver point of view. It is very comparable to WRF, and it's used in several countries by weather services, and somewhere over close to 100 research groups in academia. So it runs on many different hardware platforms, and in my opinion it's a very well managed consortium, and this turned out to be very important to have for the software efforts that I'm going to talk about. Because when you work on a community code, you can change the code, but eventually you need to get adoption back, and that turns out to be a big challenge. And so having a good consortium to work with turns out to be a very important factor. Now, the details of the calculation of Meteo Swiss is they take the global simulations that I showed before as input from ECMWF. Then they run a regional model at 7 kilometer or 6.6 kilometer scale, and then they run a high resolution model over the Alpine region at 2 kilometer scale. This is the model as it was running until this spring of this year. And so that was the old baseline, you can say. And then from these simulations, they create a number of products that some you see on TV, others is related to air traffic control or disaster management. Now, 2 kilometers, this high resolution is given by the necessity to go to this high resolution here is given by the orography over the Alpine region, and 2 kilometers is what they were capable of doing some 4 or 5 years ago when the model was introduced. What I'm going to show now, there is actually a scientific case to go beyond these 2 kilometers. So Meteo Swiss has been developing a model. What we see here is 2 valleys, one north of the Alps, one south of the Alps, that are known to be determining the microclimate. So how winds develop in these valleys really is determining the skill of your being able to predict these winds properly is determining the skill then of your weather forecasts at the local level. What we see here is the wind forecast. So this is the measured wind strength, and this is the forecast of the 2-kilometer model. And you see that it's doing rather well qualitatively, but there is a quantitative thing, that it's a quantitative problem that it turns out gets fixed if you, in this case, double the resolution. And there are a number of studies that show that going over the Alpine region, going to this kilometer scale or maybe even sub-kilometer scale is really fundamentally improving the quality of the simulations. So that is one thing that we need to do. They want to do is go from 2 to 1 kilometer resolution. The other thing I had already mentioned, that the necessity to do ensemble predictions. So you want to do the simulation and you want to do it multiple times. And again, there is an example for this. So this is a precipitation forecast over Switzerland sometime last summer. And we are going to focus on one place here in the Bernese Alps. And you can see the single run that they are doing with the 2-kilometer model is giving relatively low precipitation forecast in the Alpine region. But when you run this ensemble, so you vary the initial conditions, and then you can see that there are a few members of this ensemble that actually predict significant precipitation, but the average is relatively low. And what this basically tells you is, that there is a chance for some drastic events happening. Not that the chance is very high, but there is a possibility. And so you start seeing these from these statistical studies. And in this case, it turns out there was really significant precipitation that led to landslides and flooding and so on. Now, the weather forecast will not be able to change these things, but at least it will be able to alert the emergency management that they have to be prepared for something happening. But from a practical point or computing point of view now, these improvements, what they mean over the model that Meteo Swiss was running at CSCS, or CSCS was running for Meteo Swiss until this spring, over this COSMO 2 model is this doubling of the resolution, which turns out a factor of 10 in performance increase, because it's 2 by 2 and then by another factor 2 for the CFL condition or increased time step. And introducing the ensemble turns out, when you do the details, somewhere around a factor 20. And then they had to increase the data assimilation part, another factor 5 over what we do today. And if you do the math, introducing this new model meant increasing the simulation performance by a factor 40. And this had to be done in 3 years. Okay, so this is the previous machine we introduced in 2012. The new machine had to be introduced in 2015. And so there's simply, no way you can do this just by taking the code and putting it on a larger machine. Because out of Moore's law, you get somewhere a factor, 2 or 3 in 3 years, okay? And then you're still missing a factor 10. And so now I will talk of how do we get this factor 10. And obviously it comes from refactoring the code, okay? And the important point to note here is we're really dealing with a rather complex code when we talk about climate simulations. The details of these are the Euler equations. They don't matter in detail. What I just want to show is we have many differential operators here. Each of them represents a stencil in your calculation that we will see in a few slides. And then everything is convoluted with very complex time integration. So different parts of this set of equations having different representative time scale, and so you can imagine that the entire code that brings this together is relatively significant, and so when you look at the Fortran code that they were running, and we were running on this system that was introduced in 2012, it's of the order of 250,000 lines of code. There is this dynamics part that I just showed in the previous equation of this, or on the previous slide. Then there is this physics parameterizations that enters these equations. So each has around 20% of the code base, and there is data assimilation and other parts of the code. So the question now is, what exactly do you do? Do you just rewrite this code, or do you somehow port it, or exactly what are we approaching? And so this is really, I think, the biggest challenge we are facing in not just climate, I would argue in general, generally in computational science. And the challenge really has to do with how we, what is our workflow when we develop applications in scientific computing. So I will try to get into this now quickly. We start typically with a physical model. So this example is a climate model. We have a mathematical description of this model that we then, in this case, discretize a grid, and then we have an algorithmic description of these equations, and then we implement these algorithms in terms of a code that then gets compiled and put on a supercomputer. And this is the canonical model, I think, that everybody will recognize. And my point here is the good thing about this model is that we can draw a line, and you can draw the line anywhere in this workflow, but usually it is drawn here, where everything below the line is a question of computer engineering, and everything above the line is a question of domain science and applied mathematics. And so this is very nice. But and it applies to other fields, so you can take material science. These are like the typical codes that do very well on the top 500 systems. You can do molecular dynamics, apply this to the same quantum many-body theory examples. And so it's really a canonical view in many areas, but it is challenged. And the reason it is challenged is because today, of course, we know we have different processors with different instruction sets and different domain-specific programming environments on these processors. And so every time you change the processor, you would have to go through this whole thing again. And that is obviously not working very well. So the main point is that we have to look at this whole workflow differently. So we still have, what is not going to change, we have physical models, we have mathematical descriptions and algorithmic descriptions. So this is something that will stay. But what we know in today's, when we develop application, is that we would like to be able to rapidly iterate between these three areas when you really develop a solution to a problem. Then we will always have, when we have algorithms to write imperative code, we have to somehow compile it, and the challenge, summarizing, is we have different architectures. And every one of these architectures will need different code and different algorithms, or every one, depending on the architecture we are using, whether it's Xeon Phi or Xeon, you need different algorithms. And whether it's Xeon or GPUs, you need different algorithms. And so this all has an impact on what we are doing. And so when you look at, this is the work we really have to do today when we talk about application development. And then you see, you know, partitioning this graph at the traditional point just above the compiler is not very practical. Rather, you can draw a line at this point here, and obviously you will have to draw a line at some other point because most of the processors and the systems designed today are not designed specifically for scientific computing, but they are commodity systems that are designed for other things, and we somehow have to take these and make sense of it. And so what I'm arguing is, when we develop applications today, when we look at scientific computing and HPC, we really shouldn't be looking at these monolithic applications that we used to have in the past on supercomputers. Rather, we have two levels. We have a level of the actual environment in which scientists develop their codes, or their models, I mean, the models and the math. And then we have, underneath, we need the tools that we somehow have to expose. These tools are not simple Fortran or C codes anymore. We need to break up applications into a hierarchy of tools and really understand how we maintain these tools. And the important message is these tools are really going to require interdisciplinary teams to develop. So they need application scientists who understand the world up here. They need computer science and applied mathematics. And I'm going to show how this could look like now in terms of this COSMO model. Now, practically, how do you go about refactoring this code? So I just mentioned, you know, the scope of the code, the scale of code that we are looking at, and then you look at the runtime, obviously, that was running on this 2-kilometer model at the time. And you see, you know, there is a large fraction of the runtime is in this dynamics. So obviously you want to focus on this, another large fraction on the physics parameterization. Unfortunately, this large fraction of the code is only using a very small part of the runtime. So we can more or less try to ignore it, at least for now, in the initial stage of refactoring. And then the refactoring project of this legacy code really turns out into rewriting this dynamics and refactoring the physics code. And the reason we treat this differently is this can be treated as a black box, but this is really the part you don't want to fundamentally change because the scientists are working with the physics parameterization. At least we cannot fundamentally change it for now. So the decision was to really be aggressive here and just rewrite the code using CUDA, for example, for GPU backends, or OpenMP for Xeon, and then here take a more moderate approach using directive OpenACC for GPUs. Now, the challenge for rewriting the code is, and this is now the question, when we rewrite the code, we can introduce tools. What type of tools, or how do we structure the problem? So what we have here is, in this particular example, we have a structured grid code that has a lot of these stencil updates. So remember these many equations with many different differential operators. Each one of them translates into a stencil like this. So this is the two-dimensional Laplace operator. There were many others. And when you now look at how this code translates into the Fortran code or C code that we have in the applications, well, you will see many loops like this. So this is a three-dimensional Cartesian grid, and this is the stencil in the middle. And the problem with this type of code is, and you know, why we end up having somewhere around 50,000 lines just to encapsulate these dynamics, is that we are really talking about two things, namely the loop logic, and shown in green, and then the actual stencil. And in a standard C or Fortran code, these things are convoluted together and then repeat it for each of these many differential operators. And that's how you are in the end accumulate tens of thousands of lines of codes that you would have to rewrite every time you have a new architecture, every time you want to say change these, the order of loops, the memory layout, and so on. And so one of the tools we would like to have is design a code, design tools that can somehow split this into two parts. And so specifically in the case, and I think I need to start moving faster, in the case of this application, this was done using C++ and template metaprogramming, which in this case allowed us to introduce a language to deal with the loop logic and then use standard C++ functors to describe the actual stencils. And this allowed us to really split these two problems, the stencils and the loop logic. The loop logic being the same across the entire application because we have the same grid used in the, so in this particular case. And then what you need is a model on how you decompose the problem, and so we are using standard domain decomposition with halo exchange, and then we decompose, so this is a piece of the entire calculation that would run on a node, and then on the node you break it up into blocks, and the blocks are then broken up into individual threads. And so having such an abstract model, decomposition model, is then important because with this you can then decide at the very high level how to map this onto different architectures. In our case, multi-core SIMD CPUs or GPUs, SIMD GPUs. And so overall, when you look at the current or the code, the Fortran code that is being used traditionally in production, and this new code, this is what the software, the hierarchy looks like. So you can see that we've broken this up into the hierarchy of tools, and the important point is that the architecture specificity now comes in as a backend to the Stencil libraries. And the front end does not have to deal with the details of the architecture. So the scientists who develop code up here don't have to worry about the architectures, but there has to be a team of people that includes also some climate scientists who worry about these tools and the backends. And so in terms of this graph, I think we've demonstrated how this can be done. Okay. Now, and there's a number of papers that document this, and I will send you the slides so you can read up all the details. Okay. So now, given that we have this, we have this refactored software system, and we have different machines. What I will now show briefly is the performance. And this is really in terms of running the full application, the full production application on these systems. So, and the performance model of that would of course be exorbitantly complicated, but I can look at the results. So what we are looking at is this current, the production system that was running up to this spring that was introduced in 2012, a KXE6 with AMD Barcelona multi-core processor. Then the state-of-the-art today, KXE40 with Haswell processors, and this new CS Storm-based system with Intel Haswell and NVIDIA K80 GPUs that we introduced in the fall of 2015. So now there's 3 years that elapsed between these two systems. And so, okay, sorry, I need to go also make clear. And then we have two implementations. We have the canonical Fortran 90 implementation, and then this refactored code that we can compare. So different machines and different codes, but well-defined problem for comparison. And then we can answer questions like, you know, run the old code on the old system, run the old code on the state-of-the-art systems, and then run the new code on state-of-the-art systems and on the GPU systems, and ask what factors do we get in time to solution from these different contributions. So one thing we can answer by looking at these two systems is, this is what Moore's law gave us, 2.8 factor, almost a factor of 3 in 3 years. This is what improvement, algorithmic improvement and system utilization, the main contribution here was going to a mixed precision solver that we could do because now we refactored the code and rewrote the dynamics, so we had full control over how we were implemented, and we are now in a position to do a lot of improvements also to efficiency of the calculations, and the general improvements to the software. So this is together, you can say almost, well, this here is almost a factor, or roughly a factor 4. We got from just general performance improvements and the port to the GPU that would now be possible because we've done this separation between architecture in the back end and the front end of the code. And so what we are showing here is really that we have comparable or even better improvement due directly to the software refactoring. And then you can even factor some of this in here because this is also due to software refactoring. And then on top, so you know, overall we need a factor 40. So in order to get the factor 40, we have to add more sockets than we had before. But it turns out, and so that gives you this factor 40x I've been talking about. But in the benefit of moving to GPU means that is another benefit that we had is that the energy to solution was going down by about the factor 3. So despite of the fact that we had to increase the number of sockets by a factor about 30%, the energy or the power consumption and therefore energy went down so much that the overall system is the same size as before. The overall energy consumption is actually lower. So we are getting now even some money out that we had to invest into power or into the power, the utilities, that we can actually now hire people who support the software that we have developed. So that turns out a good bonus. And but my main point back to the discussion I started is this question of baseline. When you look at the old code running on traditional architectures or the new code running on you know, whatever best architecture we have today, which turns out to be GPUs, we have here a factor 11 between the two. And so that comes back to the question I asked in the beginning of the talk, you know, what is the baseline, the current Fortran code base, and this is a professionally maintained code, so it's not you know, it is a legacy code, but a professional and well-maintained legacy code. Or is it this new refactored code that can take advantage of modern architectures that we have today? And the difference between the two is roughly a factor 10 in terms of performance of the model. And now going back to this slide, you know, I said, I hope I convinced you we need a factor 100 when we go to the exascale systems, based on this goal of doing kilometer-scale climate simulations. But the factor 100 is based on this refactored code. Okay, so this assumes we have already done the homework at petascale today, which is not clear for most applications. And then when we look at really, you know, where are we going to get this factor 100 from? This is taking COSMO. We have another global climate model that is comparable well, we may have another factor 2 in strong scaling that we haven't exploited yet. We may get another factor 3 from going from the GDDR to the high memory bandwidth, newer GPUs. And we may get another factor 2 in hardware. I know maybe this is too pessimistic. Maybe we will get more on hardware. But when you do the numbers here, then you see we're still somewhere a factor 10 away. And this is over this improved baseline. So if you haven't done the homework, you're more than a factor 10 away. And so the general conclusion that I hope to have convinced you, it is not easy to define exactly what the goal is for Exascale if we are not using flops anymore, but use application performance. And the question that I'm raising, is it realistic to have these systems, the systems we need by 2020? That's, I think, what China promises, and Japan and the US will come 3 years later. But we will be measuring the success of these systems based on this performance, application performance that the examples I've given today. And the answer in the end depends on the baseline. So if you're saying, well, we will improve the factor 100, but you're starting with a very poor code base, then you will reach the factor 100 because you can repeat the work we did here. Anybody can repeat this work, and you get a factor 10 out, even without fundamentally changing the systems, just getting ready on petascale systems. But for sure, in the end, if we don't define Exascale just as a factor 100 over what we do today, but as something we need to solve a specific problem, then we will, in our case, we definitely need at least another factor 10 beyond what is promised on Exascale. So I hope the journey is going to continue in terms of improving supercomputing systems, but certainly we will also need to think outside of the box for the solutions, to do this in a timely manner. So thank you for your patience to listen to this talk. I think I don't know, you haven't been warning me, or I don't know if I'm running over or so. What I would like to end is with advertisement of a conference we run in Switzerland in scientific computing, and the next one of these past conferences is going to be in Lugano in June 2017. And one thing special about this conference, it is focused on trying to bring together scientific, computational science and computer science and applied math. And it is endorsed by SIG HPC, so we have a papers track on that will be published in the ACM digital library.
Okay. So thanks, Thomas, for the very insight, like from applications to systems, trying to put the complete thread together. We have time for some questions. Any questions? Yes. Please.
Can you quantify how much effort it took to do the code refactoring? How many person months or person years?
Yeah, so that's a good question, and we are working on the details of that as we speak, because I have to sort this out myself. Roughly, a very rough order of magnitude estimate I can see from the programs that were, we had to hire people, we had to invest and run projects. And the amount of effort is somewhere between 2 and 4 million Swiss francs. The reason I'm not sure at this point is I have to go really in and say, what was really the research part of these projects that we just funded for the sake of research, and what was really the part of the project we funded to actually get to this. So it is a substantial effort, 2 to 4 million on an application spent over about 5 years. But if we did not do this investment, we would have to have a system that's a factor 10 larger. Okay? And as I said in the beginning, weak scaling is not a problem in this case. We could, instead of spending 2.5 million, which we did on this system, that in the procurement, we could spend 25. And instead of spending a few $100,000 on power, every year we could spend 2 million every year, and we could still solve the problem. And so the investment is substantial, I agree, but compared to the investment in buying machines and in power, it turns out it pays off. So the return on investment is even more substantial.
Okay. Any other questions? Yes.
Ignacio Laguna from Lawrence Livermore National Laboratory. Do you have codes or applications that are using the partition that you mentioned between the loop logic and the stencil logic? Do you have code teams or applications that are starting to use this new pattern? Or
yes, definitely. So in this particular case, the example I showed you of this library that's also published in an SE paper from last year is actually the production code now on the Meteo Swiss system. So this is a real, a full climate model that is using this. Now, we are, the way you have to see how we did this, we went in 2010, we started with this whole project. And we went with the current product, so to see this idea on what you have to do is not very hard. Afterwards, really implementing this, that's the hard part. And we also had to be timely in terms of delivering this new system. So we had the first implementation, and that was published last year, and is now in production. But we are rewriting the whole thing, because once you've written the first version, you all know. You see all the mistakes you've made, and so you've done, and then you have to rewrite it again. So we are very serious about this, and we are so there is a new library that we are developing, grid tools that will implement, make a cleaner implementation. The reason I'm mentioning this, because besides breaking this up into different parts, one thing that is very fundamental is that you understand the things you have rewritten, these tools. You really understand how much effort is in there to rewrite them again. So you have to, these stencil libraries are of the order of 40, 50,000 lines of code. And it turns out refactoring, a good programmer, knows what they are doing, and assuming we have a good test environment, so unit tests and regression testing, and so this whole thing is embedded in, a good programmer will rewrite somewhere around 20,000 lines of code, 25,000 lines of code per year. So a library of 50,000 lines of code needs of the order of 2 people to maintain it. So, and I say 2 people because when new architectures come and you have to rewrite the thing, you can do it in a year, roughly. And so that's one of the key points, that, one is the code, but the other one is the efforts behind it that you need to understand to maintain. And of course, you know a lot about this with MVAPICH. But I'm saying that the same thoughts that you need to have at the low level, we also need to introduce now at the application level. And we should really go away from these single heroes who maintain million lines of code. I don't think that's a very good model.